Welcome back. My phone inexplicably turned off. So, unfortunately, I've been talking for a while. So, this is more or less where I think we left off. So, let's say it's room temperature. You have the particles in the balloon bouncing around. How hard they hit determines the shape and size of the balloon. And a thing worth pointing out is also that there are air particles. That's a TI on the outside that are also banging against the balloon. And they are also more or less at room temperature. So the size and shape of the balloon is actually defined by the interaction between these particles. If the air particles push harder, then the balloon would collapse. If the particles on the inside push harder, then the balloon would expand. And if they both push harder, then the balloon would stay the same shape. There it is. All right? So the size and the shape of the balloon is actually defined by the interactions between the particles inside the balloon and the particles outside the balloon. So now, again, if we put a poorly drawn Bunsen burner underneath, and we light it on fire, what's going to happen to my Kevlar rubber balloon? Well, the idea that I want to have in our heads here is that assume that I'm basically only heating up the particles inside the balloon. Yeah, but there's air particles passing by the flame and they're getting... Yeah, I know. So again, let's just assume that we're magically only dealing with the particles inside the balloon, the air particles that are inside the balloon, not the blue air particles outside the balloon. So what's going to happen? Well, outside the balloon, no change. The blue air particles are going to bang around, again, room temp amount, because I'm magically not heating them. But I am magically heating the particles on the inside. So what's going to happen to them? Well, again, instead of going this fast, they're going to go this fast. And instead of banging that hard, they're going to bang that hard. And instead of banging that hard, they're going to bang that hard, right? Now, what that means is, from the inside, they are banging out against the balloon harder. They have more energy. The ones on the inside are pushing harder, and they are going to bang against the balloon. But the blue particles, the particles on the outside, aren't pushing any harder. So what we're going to end up seeing is, we're going to see the balloon actually expand. Because these particles will hit so hard that now the balloon can stretch out. So what we would see is this particle would actually stretch the balloon out to this new size. And this particle would actually stretch the balloon out to this new size. And this particle, well, never hit the side, so it's not going to do anything. And then at this new size, how hard they hit is then going to match the air particles who are hitting again at the same amount. Remember, we are magically not hitting or not warming up the outside air particles. We are magically only heating up the inside air particles. So they are going to stretch the balloon, and they're going to keep stretching the balloon until how hard they stretch this balloon and hit against it matches what the air particles are still doing. So if again, what happens when I turn on my Bunsen burner? That it means that the temperature is increasing. And what happened to the volume? Again, volume is how much space something takes up. What happened when I heated it up? The volume increased. So if I heat something up, the volume increases. Again, you heat it up, volume increases. And it turns out that it's directly proportional as long as you're using the temperature the temperature, in degrees Kelvin. So if you heat it up, it is going to get bigger. If you cool it down, it's going to get smaller. And however much you heat it up, it's going to change the exact same amount. So these are actually directly proportional. But what if I cool it down? What happens then? That's a really good question. So now instead of the temperature going up, what happens if we put the temperature down? So we put the whole thing in a magical freezer that just freezes the inside ones. Again, I want to keep the outside temperature more or less the same so that I don't have to do complicated math. So if I put a magical ice cube in here, and that magical ice cube again, put a little drizzle, and there we go. It's supposed to show that it's melting. Now what's going to happen is the air particles on the inside are going to cool down. Again, this is magically just cooling the particles inside the balloon. The air particles I'm not affecting at all. They are going to go the same speed. So if I magically cool these air particles, then what's going to happen? Not only are they going to shorten back to their original length, they're going to shorten even more. Oh, look at him. He's a real guy. And this guy, instead of going back to his original length, he's actually going to shorten even more. And this guy not only passes his original length, he shortens even more. So by cooling it down, I'm lowering the kinetic energy of the particles inside the balloon. So what's going to happen to the balloon? Oh, it's pushing less out. And the outside particles are pushing just as hard. Again, the blue particles aren't changing their length, aren't changing the amount of kinetic energy that they have. So that the balloon is actually going to shrink. Because the air particles, which are still pushing the same amount, are now fighting less force on the inside. So they're actually going to win, and they're going to push that balloon inwards. So the air particles are going to actually start winning for once. It's about time, air particles. And they're going to be able to collapse that balloon. Again, these guys are still room temperature. The blue particles are going to push the same amount, but now there's less resistance. These guys are moving less. So what originally would have had the balloon, the pressure from the outside, the air particles on the outside, what with regular temperature would have been here. Now they're pushing just as hard, but there's less resistance. So that balloon becomes smaller. So as the temperature drops, what we see is that the volume drops also. And again, mathematically, that is directly proportional. So if the temperature drops by this much, the volume is going to drop by that much also. So turns out that pressure and temperature, along with volume and temperature, are proportional, which means however much we change the temperature, that's how much the pressure or the volume is going to change. Now, normally we would keep one of them the same. So we would keep the volume the same and then muck with the temperature and watch the pressure change. Or we keep the pressure the same, muck with the temperature, and watch the volume change. Right? Because when you have 3 moving parts, that's just a lot of math. No one wants to do that much math. Come on. So we tend to keep one the same and then muck around with the other 2. So, seems like it's time to answer the point. Let's get this convoluted, crazy Kevlar balloon out of here. And if I remember correctly, which I rarely do, it says pressure and temperature are, and I'm going to put in directly proportional, because I think hopefully by now that idea of directly proportional versus proportional makes sense. Remember, directly proportional means however much one changes the other. Proportional just means that they both rise when they rise, but they don't necessarily have to rise or shrink the same amount. Directly proportional means they are mathematically equal in their change. Are directly proportional in gases. And the person, of course, who figured that out was a guy with the last name Gay-Lussac. And volume and temperature are also directly proportional. In gases. Yay! So, it's super easy to remember because they're the exact same answer. Yay! Which is why I pair them together. Okay, that's all I got for you today. Good luck.